Okay, well, I think we can probably get started. Thanks everybody for joining us today. This is our presentation on automated energy analysis and early stage design presented by Sarah Mohammedi. This event is co-hosted by the AIA East Bay Young Architects Forum and the Committee on the Environment. The presentation will provide 1 hour of AIA credit, so please email info@aiaeastbay.org with your name and AIA number. I'll drop that email in the chat as well. If you have any questions during the presentation, feel free to drop them in the chat and I can help moderate that. Or if you want to turn on your microphone and interrupt Sarah, that's fine as well. Sarah Mohammedi is the founder of Build Synergies, a platform which automates daylight simulation, energy simulation, natural ventilation, thermal comfort, and life cycle cost analysis. Sarah received her PhD from the University of Texas at Austin and has been a building scientist working as a building performance analyst for the last 6 years. Sarah, thanks for joining us and take it away.
Yeah, thanks. Let me share computer. Are you seeing? Yeah?
Yep.
Okay, that's great. So let's start. Thanks, Daniel, for the introduction. As mentioned, today I'm going to go over the energy analysis and automation, the early stage of design. So this study actually is provided by Build Synergies, which is a platform that automates energy analysis, daylighting, and thermal comfort. So we can perform a series of energy analysis for different building components such as envelope, HVAC, plumbing, electrical, and renewable energy. And we can analyze different alternatives in order to figure out what is the optimal energy efficient solution can be. However, it's not just about performing the energy analysis, but it's rather about how much influence the analysis can have on the final product or on the final project. So it's about influencing the project. Just this graph here, it just shows the different stages, and the blue line shows the cost of construction from pre-design all the way to construction phases. So we have pre-design phase, and then we have schematic design, design development, construction development, then construction. And the purple line actually shows the opportunity of influence, which is going to be very early on. And then as we get to the design development construction, and as the design progresses, the amount of influence that we can have is going to get lower and lower. And also, it's not just about the cost of construction. Also, it's about the cost of energy analysis. When we get to the design development and construction development, we have such a heavy model, then we have so much information and data to feed to the model. So it's very time consuming to do the model at DD and CD. So what we are suggesting is that we are encouraged, to apply the design strategies very early on because the cost becomes very significantly high. When does energy analysis usually start? In our experience, we are hired very early on at SD, but we just wait and see to see if architects, wanted to come up with a shape, and it should be statistically pleasing, and the window to wall ratio, and they're playing, with different functions and how it connects to the urban context and so on. So we just, even though we are hired early on, but we're going to get involved maybe between SD and DD when the shape is already formed. And most of our robust work actually happens at DD and CD. And most of the projects are eager to achieve LEED or other sustainable programs like Living Building Challenge and so on. So as you can see in the graph, when we start later, which we do, we can't really be that much influential, and everything is very expensive regarding energy costs or even the cost of construction. So I just want to give you like two typical projects that I have done and how the process just went on. So this is just a luxury office building in San Francisco. And on the graph, I think at the bottom, I just show that we started this project between SD and DD. The project is like full glass. It was 4-story. And in the chart, you can see that we have different alternatives. And then on the y-axis, we have EUI. So you can see that we have provided them the Title 24 baseline, ASHRAE baseline, which is for lead. And then we, modeled the project itself, which had the window wall ratio of 60%. And then we did consider different construction. We were able to lower the energy consumption. And then we did LPD analysis, lighting power density. We lowered that. And because this building has a lot of exposure to the east and west, the architects came up with some sort of like really fancy themes, or maybe some sort of screens or some sort of they were thinking about different scenarios on the east, some sort of window treatments on the east and west. And then we come up with a more advanced system, such as like VRF system. And then we propose a spandrel panel on the lower part and on the higher part to just see how much that would impact. As you can see here, the most influential one was VRF, and surprising to the architect, they saw that their fancy screens didn't really work out. We didn't really actually discourage them to have them because it wasn't surprising for us. We just told them it doesn't impact the energy, but it's very crucial regarding the visual comfort. So, so basically we're able to do a bunch of energy analysis for this project. So this is a second project, it's a school in San Jose. And again, we were hired at SD. We just wait and see for the architects to come up with the footprint and like the shape, the overall shape of the building, how how much window they want to have. At the time, we didn't really have the placing of the zones, but we were able to run some simulation for them. The shape was very complicated. So you can see we did a VAV system for them with, in the beginning, we just did lighting power density and see how much lowering lighting power density can help. And then we did, mechanical option. In the beginning, maybe I think it was SD, they were thinking about having heat pump, heat recovery chiller. So we did that for them. And then we just proposed radiant system, connection of that heat pump, heat recovery chiller with the radiant system. But between SD and DD, they changed their plan. So I know usually that doesn't happen, but they didn't know what they wanted, I guess. And they just figured out that in the campus, they had a central plan, which everything has been renewed recently. So all the chillers had like really high COP. So they were thinking maybe it's cheaper for them to connect to the central plan. So they wanted us to change everything, all the system, connected it to central plan. That was very exhaustive to do. It was very expensive to do. And then we repeat, the scenarios again. We consider spandrel panel, then we consider displacement ventilation, radiant system, this combination of radiant displacement. Then we consider heat pump hot water system for them. And then at the end, we just propose how much PV panels they need in order to offset the whole energy, because they want it to be net zero. So these two examples are just provided for you. You can see that we started between SD and DD. Really, most of the work is going to be done between SD and DD, even though we started, we were hired at SD, but we were not really involved with the architect to give them any sort of feedback. So the disadvantage of so the other thing what I want to mention is that for those two projects, those two projects were very expensive projects, and we had enough budget to run different alternatives for them, even at DD and CD. So those maybe not very typical one, but so they had enough budget. So the disadvantage of the current tradition of energy analysis is that, as I said, we start a little bit late, and the design, the parameter, and the envelope is already shaped and solidified, and any change can be very costly to do, or the architects are not really interested at that point to apply any changes. So everything is locked in. And the analysis that we have done, like, handful of analysis that we have done was not automated. Basically, we had a full model there already developed, and then just changing that for the client. So it's very costly to do and very inefficient. What we are suggesting is that basically, instead of doing everything at DD or CD or SD or DD, we have to do it, we have to do it in the pre-design phase, which we never really get involved because the architects are just, sitting around, getting their pen and start drawing some lines. We usually don't have contact with them. I mean, they may give us a call and then we give them some answer based on the wisdom and experience that we had so far, but we don't really run simulation. So what I am suggesting here is that maybe we have to do our robust or more work at pre-design. And so what if we just provide some sort of tailored, encyclopedia of energy analysis for them, for their project? Maybe just, a guidebook with the limited information that we have, such as area, number of stories, function, and location. If we have the footprint, that's fine. But if you don't, as long as we have the area, we are set to go. And then they can refer to encyclopedia whenever they want. It's just accessible to them, whatever they have question as they are drawing and having their own discussion with their own teammates, they can, get the answer. So the other thing is that the interactions also sometimes becomes messy and complicated. And there are a lot of stakeholders that they are in the call and they get involved. And so the interactions are lengthy and maybe sometimes uncomfortable for the architects to call us 4 times a day and ask a question. So we have to set up a meeting and they're going to ask us a question. And because I already have like a full model, it just take maybe 2 days for me to just feed what they want into the model and run the model. So it's not a very straightforward relationship there. So what I'm suggesting is that what if we have that encyclopedia pre-design, like as soon as we know that we have a project, then we can just go ahead and just provide them that handbook, and then they can have easy straight access to that handbook, and whenever they have questions, just refer to it and find the answer by themselves. But if they want to give us a call, that's fine. But I think that's easiest probably for them as they are designing, having their pen and drawing on the paper, they can figure out their own answers. It doesn't mean that we're not going to have our messy relationship and interactions, and we are not going to involve other stakeholders. We're still going to have that. But just I'm suggesting that maybe if we can just a little bit start sooner, give them that information, go over that information with them, it's just more clear for them and they can make more informative decision. Yeah, so such database I'm talking about such analysis can be automated and be provided maybe in less than a day. And the other advantage is that they can make that decision with little interaction with the energy analyst. So let's go over some examples that I have done. So we have a client that they had office and branches in all over United States and also in all over the world. So for them, they want to actually come up with some sort of guideline, to follow in their design. So this is just an office building in San Francisco, and we did a bunch of scenarios. I think we did maybe 150 different scenarios. We just get together and they talk what they wanted and what they were interested very early on. And so we had roof insulation, roof reflection, U value, like what about the insulation? Maybe the insulation can be inside or it can be outside. What about if you have a wall mass, the orientation? And then we did the window wall ratio for them for the south side, north side, east and west, and all sides. And then solar heat gain coefficient for them, and then maybe some shades on the south side. So you can see that we have so many alternatives to go through. This is just the result. So what you can see is that on x-axis we have different scenarios. I just gave them the number because at the end there are so many scenarios. You have to give the number because you cannot put the name there. Just so many alternatives. So and then on Y we have EUI. So and each dot represents like different scenarios that we have done. So for example, here in San Francisco, regarding envelope, you can see that the most you can have like wall mass ratio can impact a lot. East-west window to wall ratio is impactful. Window to wall ratio all sides on average does matter, and also the U value. The rest of the envelope doesn't really impact that much, and it's because it's in San Francisco and it's a very mild climate. So the other thing we can provide them is just, show them each run how much. Basically, what we wanted to communicate with the architect is that how a change in one parameter, either increasing or decreasing it, like for example, a U value can impact the EUI, and how big and how prominent that change is, because for them, they want to invest their money. So maybe, for example, on number 3, from run 0 to 1, there's a huge difference, but from run 3 to run 4, this is the U value 0.4 to 0.3, doesn't really that much, you cannot see that much of a change. So maybe they don't want to invest their money on that. Maybe they can put their money on some other strategies. So here I'm just highlighting the scenarios that matter there. And this is just a breakdown of energy, just give them a view of like for these clients, and you can see that the lighting and equipment is really high. It's just because they had their own requirements. So it's like 30% for lighting and equipment. But so you can see that they can, if they wanted to save energy, actually it comes from the lighting and equipment. They were not interested in lighting, which was interesting. They were not interested in lighting, but they were willing to consider lowering their equipment loads maybe, and then having like some sort of advanced, efficient equipments in the building. So I repeated the same energy analysis for them for different climate like Chicago. And, it's the same thing, but here what you see is that in Chicago, most of the envelope option matters, when you compare to San Francisco, it was like maybe a handful, but now you can see that most of them for for Chicago matters regarding energy consumption. And it just gives you a comparison of between Chicago and San Francisco. And you can see that the Chicago is just blue line, and then San Francisco is purple. And Chicago energy consumption is higher, which is understandable. It's just harsh climate comparing to San Francisco. And so here, what the other thing that I want to discuss is that even the change sometimes is higher in Chicago. For example, this like how prominent it can be. Like for example, for number 10, which is like east-west window to wall ratio. As we are increasing the window to wall ratio, both of them increase, but in San Francisco, maybe it's just like 2 or 3 points of EUI, but when it comes to Chicago, it's like 5 points. So you can understand like how much it can be impactful, the envelope options. Yeah. I don't think I have much more to say here. Yeah, so this one is doing the same energy analysis like automation, but having like advanced systems such as like HVAC system will be complicated. Having HVAC system and combine that with natural ventilation, having different set points, having different equipment loads. So for example, for this client, we did VAV, ground condenser, earth tube, fluid coolers, evaporation cooling, desiccant, night flush. Turn down ratio, we were thinking about lowering to turn down ratio, the VAV valve, and see how that can be helpful. And then set point, I know we don't really change the set point, but they were thinking about resiliency and what if we have power blockage, and then they want to see how much the energy consumption is and how much they can survive without, being connected to the city. And then of course, the equipment loads. So this is the result. I'm just showing here. And this is just, yeah, so we can see that if you have ground condenser, that's useful here, but if you have earth tube, not that much. Desiccant doesn't really help. Night flush at night, if you have some sort of natural ventilation and flushing, there, it seems helpful in San Francisco, and the weather is good, so you can definitely do that. Evaporation cooling helps also. 10-down ratio, number 7, it helps. And then we can also increase the set points. The EUI goes down, maybe not that much, but it does. And then you can see the most important one actually is the different MPDs. We can get 2 points, two EUI units there for equipment loads. Let's see. So we can basically, what I'm saying is that we can do this systematic energy analysis, this sort of like automation in each design, in each phase of design. So you can do it in pre-design when you don't know nothing about the project, you just know the area and probably the location. And then when you get to the schematic, probably you know what shape you want. Maybe it's H shape. And then when you get to the design, development, construction, everything is shaped. Your zones are there. The envelope is there. There's not that much of a change there. So the blue line actually shows the number of iteration that can be possible early on. And so as we get from pre-design to construction, the number of iteration gets lower and lower. And then when it gets to construction, you have probably one scenario to run, and that's it. Yeah. So so what I'm suggesting is that we have to focus more on the pre-design because it's cheaper to do it regarding the energy cost. The analysts do the energy analysis. It's cheap. It's very fast. It's just you can get it, in a day. And when you are doing your climate analysis, you can have that as information. And then it's very accessible, easy access, direct, and then it's impactful. So you can be more influential if you applied very, very early on and inform the architects about their decisions very, very early on. And the other thing I want to mention is that not all the projects have enough money to run the energy simulation, or not all the projects are interested in LEED, but they have enough money like to do the pre-design, energy analysis, and why not doing it? I know that LEED has 1.4 doing this sort of like box shape scenarios, but it's not. What I'm suggesting here is automated, and it's like considering all sort of alternatives. But again, not all projects go to LEED. It's going to be very expensive, and we can do this sort of analysis for office buildings, for a house, for whatever, and we can be really impactful. Yeah, that's it. It was quick, I guess.
Awesome. Thank you so much. Now, I think with, all residential buildings in California now have to be net zero, and all commercial buildings will be net zero by 2030, which almost seems like not soon enough based on the way climate change is going. But I see all of these things as becoming more and more essential. And like you said, earlier is better. I think we've been hearing that for years for coordinating with consultants. Earlier is better. If bringing on contractors, earlier is better. So a lot of that comes back to how do we convince clients to start to bring on different stakeholders as early as possible. But I think this clearly shows why it's so important. It looks like we have one question in so far. Says, don't you run ML to perfect the result after certain amount of runs? The other one is difference between what you offer to platforms like COTE tool is. Last zone perimeter depth of showcases you shared with us is a question to me. So I guess you can read that in the chat, but can you tell us a little bit about the differences between what you've shown us and maybe a tool or platform like COTE tools?
I've used COTE tool maybe once or twice. Again, when you are using it's almost the same thing. You can have different shapes. You can play with the width and height of the building. I'm pretty sure, I'm not really sure if they have advanced HVAC system there. Maybe just a handful of like maybe VAV system or so far. I'm not really sure if they have turn down ratio. You can play when the energy analyst becomes the programmer and use the coding in Python in order to automate things. It's just different than when you are using just out of the shelf energy tools, because still there's some sort of limitation comes with the energy tools. And like if you want to come up with, like, for example, we come up with the turn down ratio, and if you wanted to tailor your scenarios for the project that you have, it's become very difficult to use the out of the shelf tools. But they're really good product too. If you are feeling comfortable using that, that's fine. But yeah.
Great. And then there's another question. Do you find that clients and architects are responsive and willing to change design if the energy analysis is done in the early stages?
Yeah, I have seen, it's not that often, but I have seen a lot of changes when we are talking with them early on. I just gave you some examples. It depends on the client, to be honest. But I have seen a lot of changes that we were able to do very, very early on. What can I can give you two examples, one successful and one not successful. The one that actually I gave, the San Francisco office building, the VRF system was the one that they considered. So that was a success story for us. They wanted VAV. Most of projects, they want VAV because the contractors are more comfortable with applying VAV in the office building or in the school, because they are just more familiar with how the system works, how the maintenance works. But if you have new buildings, you can offer VRF system and just be more energy efficient. So for this client, it just worked. But I had another client, so we did a bunch of energy analysis for them also. And at the end, they didn't choose, I think it was VRF system, and the contractor actually was on the call. So we did also not only the energy analysis, we did life cycle cost analysis, which we didn't really talk here, because again, it's not just about energy consumption, it's about the cost and over the whole lifespan of the building. And sometimes when you get surprised that not all the energy efficient scenarios can be efficient if you consider the whole life of the building. And for that project specifically, it was a medical office building, and the contractor was there. So the contractor was supposed to give us the number for the life cycle cost analysis. When we did the energy consumption, we just showed that, okay, for example, VRF makes sense. They had a bunch of them. And then the contractor asked us the Excel or whatever we are using. And then they basically, I think they played with the numbers in order to show that the VRF doesn't work. So it was so drastic that you could see that the VRF system now it's not working because it's too expensive to run or to implement. So at the end, they didn't end up with VRF because the number, the cost, the life cycle cost analysis didn't make sense. The energy was there, but the life cycle cost analysis was not there. So that's sort of like the messy interaction that I'm telling you is just like, it depends project by project. Sometimes you have contractors. Sometimes, people are more flexible. I found that if you can make a case with the architects, not just about the energy, if you can tell them like, if you use this design or this design alternative, it's not just about the energy, it's about the visual or thermal comfort. They are more willing to adopt that because they want, the occupants to have a great experience, inside the building. So I found that if I make a case for some scenarios, and it's not just about the energy efficiency, it's also about the thermal comfort and the visual comfort. Usually, the architects will accept it.
Yeah, definitely. Liam has a question, says, I'm curious why adding earth tubes resulted in more energy being used than the baseline. So I don't know which slide that was.
That was something that we discussed about it. But to be honest, we couldn't figure out with this project why it didn't happen. What was that? Yeah. Yeah, we had this discussion. You can see that all other scenarios worked, and for this earth tube, it didn't work. I think maybe there are some, because there are objects in Energy Plus, so maybe we need to put more attention on the default numbers. I actually went there and I checked the numbers. It seems fine, but to be honest, we couldn't figure out why the earth tube is going. It's just higher. It's 2 points higher. Yeah, that's good observation.
And have you started to look into how embodied carbon is also affected by different strategies?
Yeah, I think that it's just like, as I said, life cycle cost analysis and the embodied carbon is very important. We can also do that in the early stage of design. It just need more information, and then early on, like if you are doing all these scenarios, imagine how much information I need to put for each scenarios, like you know, the feed for like how much embodied carbon is going to be for each like equipment load. It's going to be more challenging when you are doing that in the pre-design, because you just don't, for equipment, like if I lowered, I don't know what kind of equipment is there to just give you the number. For some of them you can, for most of them you can, but some of them it's very hard to come up with that number. So maybe I can suggest, maybe you can do it in SD. It's just too many information. And I never really had that much of information to do it at pre-design.
Yeah, a lot of details go into that,
yeah,
for sure. Isaac has a question, says, as an architect, can I double as an energy analyst once trained and incorporate the energy analysis in my architectural designs?
What was the question? If he can learn?
Yeah, if architects should take it on to become energy analysts themselves so that we can incorporate these types of strategies throughout the
Yeah,
design
actually I've seen a lot of architects who are really good at doing energy analysis. Not all of them, like you have to have a really good background in like physics in order to understand, like if you have solar heat gain, if your solar heat gain goes up, what happens to your HVAC loads and your lighting and your heating and cooling and your fan. You have to have some sort of understanding of physics and dynamics, and doing this sort of analysis needs also a little bit of coding. So there are a lot of architects who already use coding in, you know, Grasshopper and other programs. So I can totally see it's possible, but you have to just understand that what is your skills are, what is your talents. Do you have talent in understanding the algorithms and coding, and then do you have understanding of physics. The other thing I want to mention is that maybe it's a little bit complicated when it comes to HVAC system. On the envelope part, on the equipment or lighting, architects can definitely get in, but when it comes to the HVAC system and what numbers you want to put in, it does matter to understand, and it does matter to have maybe some consultant on the board when you are running the simulation. I remember that early on when, was it Safari? Yeah, I think it was Safari. So the Safari came in and the architect asked us to just, you know, run the simulation and run our simulation and just compare that and see that if it works. And we just noticed that there were a bunch of input and default numbers in the HVAC part that didn't make sense. It was very I think it was 5 years ago. So I don't really use Safari now. So maybe they get updated and they fixed it. But you have to have a very sharp eyes, to notice these problems that is embedded in, out of the shell software.
Definitely.
But yeah.
I found it very fascinating that maybe the architectural envelope impacts are not very effective here in San Francisco, and it really, we need to focus more on some of the MEP systems, whereas in Chicago, where you can really have a big impact is through the architecture.
Yeah, I mean, I already knew that, in San Francisco, it's just mild and Chicago is just harsh. I already knew that, like, okay, so the impact is going to be higher, but I never really thought that the envelope really matters in Chicago, but maybe not that much. You can have all glazing here and don't see that much of a difference. You can offset that, but like putting some PV panels up there.
Yep.
So it's just like you are just dealing with different climates.
Yeah, I'm wondering, as wildfires become more prevalent and PG&E does more intentional shutdowns and blackouts, how that's also kind of plays into this. You talked about the night flush, which I think is it's been something that local people have done in the Bay Area, for centuries probably. But the idea of opening up at night and being able to take in all that cool Bay air, but you can't do that when it's smoky. And so our building's going to have to start to adapt to that as wildfires become more and more frequent.
Yeah, I mean, you can have some sort of sensor to detect if it's not, comfortable, and you really don't open the windows or turn on your economizers. But the resiliency, I think it matters. And as we go, I mean, I'm pretty sure, as we were talking in the beginning, the title, like California is going toward net zero. For housing, we are already there. For office building, we're going to get there sooner or later. So the other question that we can ask is about, like, the resiliency, as you were talking about. Like, what if just we have electricity blackout? And so that's why, like, for this client, they were interested in that. They were questioning about what happens, how long I can operate my building if there's a electricity blackout. And we were just doing that analysis for them. Like, they wanted 3 days, so you have to have like PVs and batteries there. And they were thinking, we were just suggesting them increasing the set points, opening the windows, or maybe limiting the number of people in this space. Like, we were, talking about them to figure that out. But it's very important, like, just, in Houston, it was in Texas, right? So it just happened that there was a blackout everywhere. So if all the buildings had the capability of running as well by themselves for 1 or 2 days, that would be wonderful. Thank you, Daniel.
Yeah, we should have you back to present again soon.
Yeah, thank
really
you.
Good.
Yeah, it would be an honor.
Okay, bye everybody.
Bye.
Bye.